Welcome back. In the last session we had completed the schematic and also we have done the error rule check. So moving forward we'll generate the netlist and we'll proceed with matching the footprints with the logical symbols. Now netlist is a way in which Kicad or any PCB design software links all the components in the schematic. So it is basically net means wire and list means a list of wires. So it's just a list of connections that it makes and keeps. So to create a netlist with Kicad, you need to click on .net icon here, which generates the netlist. Now this netlist can be used with even OrCAD PCB, 2CAD Star or Spice to design the layout, but we'll be designing it with the PCB new, so we'll keep the default format and we'll click on netlist. So it will create a file with the project name Arduino with Kicad, and the extension would be .net. Alright, so once the netlist is generated, we'll go back to the Kicad main window and we'll open the CVPCB tool. So this is the tool which is used to match the components. It would throw up an error, but this is fine for if it is a new netlist file. So you can just click on OK. Now to make things simple in the tutorial, what we have done is we have created a .mod file which keeps all the modules that are required for this particular project, and you can download the entire project from the tutorial page. So before you proceed with this step, it is recommended that you copy the .mod file in the project folder. So this is the explore labs.mod file, which has all the modules required for this project. We'll copy this and keep it in the project folder. So explorelabs.lib is the components file and explorelabs.mod is the footprints file for this particular project. Now there are various ways to make footprints for components. So you could manually create footprints, or you could download footprints from the internet. All those topics we'll cover later. Assuming we have all the required footprints, we'll proceed with the design. Alright, now we need to link the footprints file with this particular tool. To do that, click on preferences, add on libraries, and then add the file which you have just copied. So this is .mod file, and you can just click on OK. Alright, so once we match the required footprints, we could go ahead and draw the layout in the layout drawing software. But before we go ahead and do that, we need to know a little basics of what footprints are and what is the right place to look for them. So usually, let's take example of the microcontroller that we have. It's a dual inline package that we'll be using, as most of the Arduino boards use. So the best place to refer is the data sheet of the microcontroller. Now if we just check the data sheet of the Atmega 8 microcontroller, so you will find packaging information, and in that you would see that it comes up in various different packages, and so these are all the packages. So we'll be using the dual inline package. So this is the dual inline package, and here you would find the distances uh, between the pins, the pitch, and all other details. Now what I would like to show you is there's a fundamental difference between the through hole and the surface mount devices. Now there are basically two ways in which the components are measured. So and the through hole components of the earlier generation, they are measured in units called the mils. So mils was the standard unit that was used earlier, and most of the dip components, so or through hole components, are still using the same units. Now it is important to note this, because if we take example of a dual inline package IC, so now what happens is the so it's a rough sketch. So if we measure the width between the pins, this is about 300 mils, and in between pins it is about 100 mils. So this is pretty common for the dip ICs. You will even get ICs which are where the width is about 600 mils. So this distance is about 600 mils. So this is pretty common with all the through hole components. And so to get an idea of what a mil is, so let's draw a simple picture. So if this distance is about 1 inch, and if you make 1000 parts of it, so 1 divided by 1000, so 1/1000th of an inch is a mil, 1 mil. So you can imagine it's a very short distance, and even some of the PCB manufacturers specify their design rules in terms of mils. So that's why we have discussed it here. Now so this is mils, and this is how it relates to inches. Now 1 inch is about 2.54 centimeter, or which is equivalent to 25.4 millimeters. So 1 inch, or 1 inch is again about 1000 mils. So 1000 mils is about 25.4 millimeters. So we'll have just this on back of our mind before we proceed with the other components. So whenever we specify something in inches, so let's make this. So if it is 0.354, so if this is the case, then if this is inches, 0.354 inches, so this place is about tenths in mils. So this is about 4 mils. So this is 100 place, so this is about 54 mils, and this is about 354 mils. Alright, so this is what the mils is. So it's not E over here, it's just MILS, so it's mils. Alright, so let's see the dip IC which we will be using. Now The DIP IC which we are going to use, it's a 28 pin dual inline package, as we have seen in the data sheet. So the distance between the two pins, that's E, which has been specified here as a small letter E, it is about 2.54 millimeters. So here the units are in millimeters. So 2.54 millimeters makes about 0.1 inches or about 100 mils. So in the same way you could find all other dimensions. So with through hole components, it is better or recommended to measure them in mils, so that you will get all round figures. So before we go ahead and assign this particular IC, we'll go ahead and look at how it looks. So this is all the ICs that you have. So this is dual inline package, so we need a 28 pin IC. Now you could see a couple of options here. So the difference is the 28 pin ELL stands for elliptical patch. So if we just look at this, sorry, so this is the parts of these ICs are elliptical in shape. So you could also opt for the round pads. So if we look at this, then this is the round pad ICs. So we'll go with the elliptical ones. Alright, so now if you could observe here, this distance, now if you see from x-axis, this is about 0.5 inches, and this is about 0.5. So total distance is about 100 mils or 0.1 inches. So, and you could also measure all the distances. It's very important that you verify all the footprints that you put in the design. So with the standard components, it is pretty common to use the library footprints, but it is always ensure that you measure the footprints before you put them in the design, because there's little that one can do after get the boards fabricated. So so we'll go ahead and put this is, and again here to match a footprint, you need to double click on the footprint on the right hand side, the option that you see here. So we'll go to the DIP IC. So it is a 28 pin elliptical pad, so we'll match that. In the same fashion, we could go ahead and match all the required components. So let us just go one step ahead and see what are all the components that we require for this design. Now as we had added the modules file in this particular tool, we could as well go ahead and add the modules file in the CVPCB tool, in which we'll be drawing the layout. This I'm just showing you in order to have a brief view of all the components at once. So in the same way, we could go to preferences, library, and here you could add that particular .mod file, explorelabs.mod. Okay, so I had already added that. So if you're doing it for the first time, you could just add the same, and you can click on save. Now if you would like to see all the modules that we'll be using in this design, then click on place a module icon here, and then you can select by browser. So, and if you go to that particular file, explorelabs.mod, you'll see all the components that are used in the design. So so let's just see this and match them back. Alright, so the capacitor, it's So the capacitor that we'll be using is all the capacitors that we'll be using in this standard 1206 except the electrolytic ones. So we'll place those and we will proceed. So what you could also observe is we have not put the values here, which you could again go back, change, and we can proceed. But looking at the design, we could also by looking at the reference number, we could go ahead and match the components. So let's look at the design now. The C1 is a standard component. So this is the 0.1 microfarad capacitor that we require. So let me just change the value here. And this is a bigger electrolytic capacitor that we'll be using. So this is about 100 UF, 25 volts. Alright, so let's just match these components. This is C1 and C2. So C1 is you could find a direct match for C1. This is a simple the distance is 0.1 inches between them, and you could also use SMD for it. So let's just use a SMD component for it, and all the packages that we'll be using for in this particular design will be of 1206. So again, these are dimensions in millimeter, so this is fairly common surface mount devices. So you could go through some of the data sheets to have a feel of the dimensions for these components. So this capacitor is SM1206. Then CP1 is an electrolytic capacitor, so that would be a little bigger one. So this is what we will be using, and this is again a 0.1 microfarad, so it's same SM1206. And then again we have a 10 microfarad, which is C1V5, and these two again are SMD capacitors. So alright, and the barrel jack is what we have here. So if this is a DC power jack, you could also see the 3D view of it. So there's no 3D assigned right now to it. So this is the one, so you could assign that. Alright, and D4 is the normal diode, or you can even use a SMD1206 diode, which we'll be using. And LED is again of the same package. So now USB is the USB B type. So this is the B type USB connector. So you can also see the 3D for it. So this is the USB component which we'll be using. And K1 is the 3-pin connector. It's just a single inline 3-pin header. So this is the 3-pin header. The distance between the two pins is again 0.1 inches, about 100 mils, as you could see here. So we'll use this. Then this P1 is the digital input. Now if you look at P1 in our schematic, so it is about 6 pins. So we'll use 6-pin single inline connector. Analog in is again 6-pin single inline connector, so we'll use it. Digital IO is about 8 pins, so we'll choose that. and the power connector P4 is again of 8 pins, so you'll choose that as well. And then there's a ICSP or in system programmer. So this is a 3x2 connector. So let's see if we have a 3x2, or we could just check what is the name of that in the design jack. So the 3x2 FRC, so it's named FRC 3x2, it's a FRC connector. So let's just match that. So this is FRC 3x2. Then this is a 470 ohm resistor, which is again of the same package, SM1206, a resistor again of the same package, and we'll be using a switch, special type of push button switch, and the package for that, let's just check here. So this is SW push button small, so we could use that. And the CP2102, again, if you look at the data sheet, so it comes in quad flat pack, so it's a 28 pin package, and the IC is very small, so you could see the dimensions. The distance between two pins, that is E, is about E is about let's see, single E, yes, it's about 0.5 millimeters, so it's a very small distance. So this is a quad pack IC that we will be using. So we have a footprint for that as well, so let's just go ahead and see that. CP2102, yes, so this is the one, so you can view it. So this is a tiny little one, so let's just choose that. And this is a regulator. It is also a surface mount device, and the package for that is this particular package. So it's LM1117, so it comes in two flavors, 5.5 volts as well as 3 volts. So 3.3 volts, sorry, 5 volts and 3.3 volts. We'll be using the 5 volts one, and this is a standard crystal. So this starts with HC18, I guess. Let's see. No, not that. This one, it's 49V vertical mount. Yes, this is the one we'll be using. Alright, so this is how we match all the required footprints. So just to note, if you do not have any components in the library, you could create them using the library editor. This we'll discuss in a separate tutorial on how to make the schematic symbols as well as footprints. And once you match these components, you can save the netlist file, which can be imported in the PCB new tool to draw the actual layout. Thanks for watching.